This is our introductory lesson to vectors. We're going to introduce the idea of what a vector is. We have to come to terms with the nature of a vector, the uniqueness of a vector compared to other things we've seen. We're going to tie it a little bit to some stuff that we do already understand, but just generally get an idea of what a vector is, what it represents. And then we're going to look at a few of the operations that we can do with vectors. Now, it's interesting, I think, similar to maybe other areas of mathematics, some things cooperate with our intuition, and some operations of vectors make sense with what we would expect them to do or to be like. So that's, again, something that throughout this entire unit, I think is really important to think about is where our intuition is correct and where it's not correct. And some of the operations that we do are going to be very intuitive, and that generally makes things easy. But then later on, not so much today, but in future lessons, we're going to see that some of the operations are not intuitive at all, and that will require more practice, more consideration. But first, we're going to start with just the definition of vectors and a couple other things related to vectors. And then we can start to work with them and dig a bit deeper. So the first thing is, what is a vector? A vector is something that has both size and direction. Often when we talk about vectors, we refer to size as magnitude. So that's just another way of saying size. And this isn't entirely foreign to things that we've done before. In fact, you could think of integers as a simple type of vector. So an integer could have a size of 5 and a direction of either positive or negative. And positive 5 goes one direction, and negative 5 goes the other direction. But in both cases, their magnitude is 5. So that is, in a sense, a one-dimensional vector, which is not something that we explore very much. We are more interested in two-dimensional vectors, and then eventually, after a few days, we're going to look at three-dimensional vectors. But that gives you an idea of what a vector is. It has a size, which is just the magnitude, just the number that's involved, and then a direction, which for two-dimensional vectors is going to be more complicated than just positive or negative, but that's one way of looking at it. Some examples of vectors. One common one is velocity. Okay, so, and this is a very big thing in physics. An important idea is the difference between velocity and speed. Speed has no direction, whereas velocity does. That's a standard definition in physics. Not something we're going to worry about too much in this course, but it's a good example. So a velocity would have something like 5 meters per second down, or up, or left or right, or whatever direction is relevant. Okay. Another one could be distance. With direction. So it could be something like 8 kilometers north. Okay, so it's got both size or magnitude, 8, and then kilometers is just the units of the magnitude, but then also direction north, obviously compared to east, west, south. Okay. Weight. Again, this is not something that we have to worry about too much in this course, but in physics class, you differentiate between weight and mass, and weight is a vector because it has direction, which is generally down, whereas mass is different. Okay. Just generally, again, this is not the stuff that we're doing with this. We're going to start looking at operations of the mathematics side of it, but this is something that some of you might see at some point. So there's two different ways that I can represent in 2 dimensions. Okay. And this one's called quadrant bearing. And let's say it's like this, and this angle is 30. This is just a notational thing, okay? And let's say this size is 30 kilometers from here to here. Okay, so we would call this north 30 degrees west. So the first thing you start with is the axis you start on, and then 30 degrees west means from the north you're rotating 30 degrees to the west, okay? And that's called quadrant bearing. The other way that these that we sometimes give vectors or direction is called true bearing. And true bearing, so I'm going to draw the same kind of vector. So again, let's say it's 30 kilometers from there to there. But true bearing always starts from the north and rotates clockwise. Okay, so this would be 330 degrees rotation clockwise from north to get to that same location. So both of these vectors mean the same thing, just different notational ways of talking about them, of stating what they are. Quadrant bearing is north 30 degrees west. True bearing would be 330 degrees, and that's just a standard that it starts from north and rotates clockwise. This is a bit awkward for math because in math, we're very used to angles in standard position that start, you would say, at the axis that's pointing east and rotate counterclockwise, as we're very familiar with. So these are very different, but they're just a couple of different ways that you might see in navigation and in different types of navigation or mapping, that sort of thing. I don't actually know which one is used exactly where, but they're both different ways of talking about vectors. Again, these are in two space. So these are on a flat kind of map you could think of. Okay, so those are some examples of vectors. Now this is important. And again, something that we're going to talk a lot about is the difference between a vector and a scalar, how they interact, and all the different operations we look at. Some of them are going to, and this doesn't have a lot of context for you right now, but it will. Some of the operations that we do will result in a vector, and some will result in a scalar. And that's going to be one of the important things that we explore and get some level of understanding with is what's the result of this operation, right? Because vectors are very different from scalars. A scalar is a quantity with size but doesn't have a direction. And I can do things with scalars and vectors together. Okay? So this is what we're going to talk a little bit about this today and continue to explore it moving forward. So some examples would be mass. Okay? And so your mass is just a single number. It has units. 80 kilograms, 150 pounds, but it doesn't have direction. So it's different from weight that way. And then speed. And this is just definitions of things in science or in physics. We consider velocity a vector. It has both speed and direction, but speed is just speed. So just an example would be 25 kilometers per hour. And there's no direction there. It's not east, west, north, south. It's not up, down. It's not left, right. It's not anything like that. It's just the speed on its own. Or you could have a distance 5 meters, no direction. Okay, so that's just a very beginning to some definitions of what a vector is. And we're going to continue to explore the kinds of things we can do with it, the kinds of things that it can help us with. One way we talk about vectors is by just using arrows. And when we use an arrow, we're just doing a vector drawing here. And again, I think this is something that's common in physics class in high school. We use arrows to represent vectors, and the length of the arrow represents the magnitude, so how long it is, which might be to scale. And by that, I mean, you might actually draw 2 centimeters, 3 centimeters, 4 centimeters, or it might just be kind of generalized that one is longer than the other. Okay. And then the direction of the actual arrow that you've drawn represents direction. Okay. So I'm going to draw a couple of arrows here, or a couple of vectors here. First one is going this direction. Okay. And another one maybe is going this direction. Now, we're going to write this down in a moment, but we can call these vectors A. When we're talking about vectors, we use a special notation which has an accent on top of it. So sometimes this is referred to as a harpoon, that little one that's got like a line and a tick mark above. And then otherwise we use an arrow. And then when you look at vector A, the harpoon above it is like got sort of half of the arrow part. Maybe it's just a lazy way of writing an arrow. So both of these are just different notations. They mean the same thing. There's nothing different between one type of accent or the other, like the harpoon arrow or the regular arrow. They mean the same thing. But when you have a letter with an arrow above it, that means you're talking about a vector. And that's going to be really important notation. We never, ever, ever refer to a vector without that accent arrow on top. If you leave it out, it's what you're talking about is not a vector, and that is not in any way okay. And so you can see that vector A is going in one direction, vector B is going in a very different direction. And vector A has a much larger magnitude. It has a much larger size than angle B. And I didn't measure these to anything specific, so I don't know exactly what they mean. But this is generally one way that you can talk about vectors. Quite honestly, it's not a very useful way, but it is something, it is one way that we can talk about vectors and refer to them. So let's write down a little bit of that notation that I just talked about. A and B, these are vectors A and B. Often we use U and V as vectors. So here's an example. There's vector U, or V with the harpoon type of arrow. Or sometimes we talk about a vector between two places. Okay, and we would call that vector AB. So these are all vectors. If we want to talk about the magnitude of a vector, we talk about it like that. It looks like absolute value. It's related to absolute value because absolute value, actually, if you think about it, it takes away the direction of a number. It takes negative numbers and turns them into positive. So all we know about an absolute value of a number is its size. And so it's not a coincidence that we're using the same notation for the magnitude of a vector as we do for absolute value. But in the context of vectors, this means the magnitude of U. So this is the magnitude of vector U. Okay. And another thing to note is magnitudes are always positive. Because negative is a type of direction. And so we don't have, I mean, you could subtract a magnitude. It's not that you can't do something negative with a magnitude, but just as on its own, a magnitude of a vector is always a positive value. So I don't know if I drew these exactly perfect, but let's imagine that they're pretty close actually, that A is twice the length of B. Now they're in totally different directions, so it's not like you're doubling one of them, but if we're just talking about the length, then I could say that 2 times the magnitude of B is equal to the magnitude of A. I can't say 2 times B equals A because that's not true. They have different direction, and this is why one of the reasons why vectors are so different is because we generally don't just double a vector. I mean, sometimes you might, but we don't just double a vector but we might double its magnitude. If we're just talking about its magnitude, and let's say A has a magnitude of 4, B has a magnitude of 2, but they're in totally different directions. So, adding them that way, like 4 plus 2 or 4 minus 2, doesn't make any sense. It's not how it works. So a lot of the basic, and this is what I was saying before about our intuition in terms of operations, a lot of the basic operations we have in mathematics that we've been using since grade 1 are very different for vectors, and they require a very different thought process and understanding to make sense of those basic operations like adding, subtracting, multiplying, dividing, exponents, all of those things, right? And that's one of the things in this unit in particular that we're exploring is how do we apply these operations? What do they even mean? What are their properties, that sort of thing. Okay. And that's big part of what we're going to do over the next few days. A couple more things quickly. We're going to talk about this a lot more. And as we're doing different examples, we're going to see it over and over again. But something that we really need to start thinking about is all of these different properties. So I'm thinking about this vector AB here. And if I go from A to B as a vector, that is not the same thing as B to A. If I think of 2 points in space from point A to point B, that's not the same thing as point B to point A. They have the same magnitude, but the vectors are not equal because they are in opposite directions. If we wanted to state that their magnitudes are equal, well, there you go. That's true that their magnitudes are equal. The distance between 2 points in space, whether it's your house to your friend's house or your house to the school or whatever it is, the distance between them is the same. Doesn't matter which direction you're looking at. So their magnitudes are equal, but the vectors themselves are not equal. Okay. However, and we're going to talk about this more soon, the negative of a vector is the opposite direction of a vector. And so I can say that vector AB is equal to negative vector BA. So vectors can be equal to each other, but in fact, 2 vectors are equal if and only if they have the same magnitude and the same direction. And AB is in the opposite direction of BA. But if I make BA negative, then that turns the direction. And I think there is something intuitive about that, although there are questions and circumstances where we sort of forget this important idea or don't use it in the right context, and it can cause some confusion. But generally speaking, I think that's a fairly intuitive idea. So let's take a look at a little example just using vectors as arrows. We're not doing a lot of this because it's not very powerful in terms of mathematics, but it does, I hope, move us forward in thinking about and understanding what vectors are. So Valerie rode her bike 2 kilometers west, then 3 kilometers south. Represent this with a vector diagram. Determine the magnitude of her resultant vector. So there's a little bit of definition in here as well. Okay, I'm going to draw it first. And I'm going to use our general idea of which direction on the page west goes. So there's 2 kilometers west. And I'm not doing this perfectly, but approximately 1, 2, 3 kilometers south. And when we draw vectors like this, we definitely put arrows to show their direction. So I'll call this vector A, which was 2 kilometers long and west. And I'll call this vector B, which was 3 kilometers long and south. So what is her resultant vector? Her resultant vector, hopefully this is something that you would guess, is the size and direction that this person, Valerie in this case, would have actually traveled. So from her very beginning, over the course of the trip to the very end, doesn't matter which path she actually took, where did she start and where did she end, that is my resultant vector. And in this case, it's equal to vector A plus vector B. Okay. R is the standard that we use for the resultant vector. So you'll see that commonly in examples like this. So that is our, if it says determine the magnitude of her resultant vector, so to find the magnitude, well, this is a right triangle, so we're going to use Pythagorean theorem. And there are other situations where it might not be a right triangle, and you might use other kinds of trigonometry or whatever to figure out what the magnitude is. Often it would be trigonometry, maybe almost always. But in this case, we can just use Pythagorean theorem because it's a right triangle. So the magnitude of vector r will be equal to, or vector r squared, the magnitude of vector r squared, the magnitude of vector A squared plus the magnitude of vector B squared. Okay, so 2 kilometers, 3 kilometers, 2 squared plus 3 squared. So the magnitude of vector r is the square root of 13. 2 squared plus 3 squared. If I wanted to find the direction, and this is something that in some cases may happen. We're not going to really do it in this. We are going to calculate directions of things, but just not in this case very often. But again, it would be trigonometry. And I would look at this as a tan question because I have opposite and adjacent. And I would use SOHCAHTOA tangent to find that angle. And it turns out in this case that theta is 56 degrees or approximately 56 degrees. Okay. And, you could talk about this as a true bearing, in which case you would have to start at north and rotate clockwise all the way around. Or you could talk about it as a quadrant bearing, and it's this direction, 56 degrees this way, right? And just one final note on quadrant bearing. It's not something we're going to really use very much, but it always starts on the vertical, which is interesting because that's different, again, from angles in standard position, which we always think of as from the horizontal kind of thing, the related angle, I mean. But in this case, it's always from the vertical. So you either start from north or from south. So in this case, it would be south 56 degrees west, because I started south and I rotated 56 degrees to the west. So that would be a quadrant bearing way of talking about that angle. Okay, so you can see how we can use little bits of trigonometry, Pythagorean theorem, in order to determine magnitudes between two different vectors and directions between two different vectors. That is something that in some disciplines of mathematics or science you might see. It's not something we're going to explore a lot in this course. Okay, some more definitions. Today's a lot about definitions, and hopefully over the course of the next several days, as we're applying these definitions and talking about them, you really hammer them home, because I'm going to go over them fairly quickly. Not going to do a lot of work here. We don't have a lot of examples, but these are all words that you need to know and know well, because again, it's terminology that we're going to use. And if you don't know the very specific and careful definition of these terms, it could mean that you're misunderstanding something or missing something along the way, right? So keep in mind, often definitions, you don't need to know the formal definition, but you do need to understand these terms. Equivalent. Two vectors are equivalent if and only if, the FIF notation that we've seen before. Okay, their magnitudes are the same and their directions are the same. So equivalent or equal, similar idea, right? And I mentioned that before, but again, that's a formal definition of vectors that are equivalent to each other. They can have the same magnitude but different directions. They can have the same direction but different magnitudes. But if they have both the same magnitude and direction, then they're equivalent. Opposite. Two vectors could be in the opposite direction of each other. That's not what the word opposite means. Very specifically, two vectors are opposite of each other if and only if they have the same magnitude, but opposite directions. So let's say I have one vector that's going this direction. Okay, and then I have another vector, and I'm going to try to draw it basically the same length that's going that direction. So I might call this vector u, and I might call this vector v. And they have the same magnitude approximately. Again, drawing these things out is obviously not a very accurate way of talking about these things because you're never going to draw them perfectly, but they were pretty close. But one's going one way and one's going the other way. So vector u is opposite of vector v. And that is one thing that we'll ask you to do. We'll say find a vector that is opposite to vector u. And you're not just going to be drawing arrows, you're going to be doing calculations. So it's something you have to know that it means same magnitude, opposite direction. Negative. Two negatives. I mentioned this before. Two vectors are opposite. One is the negative of the other. So that just means vector u is equal to negative vector v. This is what I talked about before. Or vector v is equal to negative vector u. And like I said before, vector a, b is equal to negative vector b, a, because they're going from the same 2 points, so they have to have the same magnitude, but they're in opposite directions, so one is the negative of the other. And as you would expect, two vectors are parallel if the directions are either the same or opposite, right? So because we're talking about two space, I can have vectors that are going in every direction. And I would say none of these are probably parallel to each other. I don't think so. No, I think they probably aren't. But if I do this, these are all different lengths. Some are in the same direction, some are in the opposite direction, but those three are all parallel to each other because they are all in either the same direction or opposite direction. Okay, so the ones on the left here, not parallel to each other. They're going in all different directions. Like I said, we're going to talk about vectors in 2 space, but we're also going to talk about vectors in 3 space, which is a whole new world. But in 2 space, I can have vectors that are parallel. This is very similar to when we talk about parallel lines in grade 9 and grade 10 when we're just looking at equations of lines in 2 space in the Cartesian plane. Right? So same idea. The one tricky thing about things, vectors being parallel, is we start to have different words for it. And we'll talk about that moving forward. But we have other words that we use for parallel. And people start to think, does one word mean something special and another word doesn't? And there is some sort of nuances to when we use one of the words parallel versus one of the other words collinear. But to some extent, they're interchangeable. So anyway, that's coming down the road. I don't think that's going to come up really today, but it is something to think about, that we have other words for parallel and perpendicular when we're talking about vectors in 2 space and 3 space. And try not to overthink it. Try not to get too confused about that when it's just terminology. So that was some basic definitions of vectors, just scratching the surface on what a vector is and hopefully getting a little bit of an understanding of how it's different from numbers we've seen before, because they can have more than one dimension. Let's take a look at some operations we can have with vectors. So adding vectors or subtracting vectors, which I think we're going to kind of do next, but adding vectors that are in the same direction. So if I add 2 vectors that are in the same direction, then I am going to have the resultant vector will be in the same direction as both original vectors, and the magnitude of the resultant vector will just be equal to the sum of the magnitudes of the 2 original vectors. So let's see if I can do this. About that far, and then another one about this far. I'll do it like that. Okay. So we'll call this vector A. We'll call this vector B. Then if I wanted to find the resultant vector, I'm going to add vector A, which was about that long, to vector B, which was about that long. So vector A went about this far. Vector B is there. And the resultant vector doesn't have to line up with those, so it could start wherever we want. Okay. Things are easy if they are in the same direction as each other. If they're parallel, it makes our life very easy because the direction doesn't change and I can just add their magnitudes. If A was 4, B would have been 3 just based on how I drew it. I drew B about 3/4 the length of A. And then R would just be in the same direction and you would just add 4 and 3, 7. So it would have magnitude 7, whatever, centimeters or whatever. Okay, so it's easy if they're in the same direction like that. What about adding vectors that are parallel but opposite? Again, this is intuitive. If the magnitudes are equal, oh, this is important actually. Let me before I get on that, let me just talk about this. This is intuitive. If I'm adding a vector going one direction with a vector going the opposite direction, then you're just going to subtract their magnitudes, right? Like this is intuitive. This is like negative numbers. 5 plus -7 gives you -2 because the -7 is bigger than the 5. So that is exactly how vectors work as long as they are in the same direction, as long as they are parallel to each other. So same direction or opposite direction, right? Okay, but here's an important definition. If I'm adding two vectors whose magnitudes are opposite, their directions are opposite, but their magnitudes are equal, that does not result in 0. It results in the 0 vector. So this is very different from 0 because it's a vector. And the number 0 is a scalar, and 0 vector is a vector. And this might seem like one of those picky things, but hopefully you've learned by now that these picky things matter a lot moving forward. So this is the 0 vector. Okay. It has a magnitude of 0. And it has no direction. Okay, and if I have, I'm just going to sketch this simply. If I have vector u and I have vector v going the opposite direction, same magnitude, so vector v is equal to -u, then vector u plus vector v is the 0 vector, right? Or you could say vector u plus negative vector u is the 0 vector, right? Two different ways of saying the same kind of thing. If the magnitudes are not equal, then like I said, the direction will be the direction of the resultant vector will be the direction of the largest vector. So same thing as 5 plus -7. The result is going to be negative because -7 is bigger as the 7. The magnitude of 7 is bigger than 5. Okay. But we can think of, but in terms of vectors, we would write it like this. If the magnitudes are not equal, the direction is the direction of the largest vector, and the magnitude is the absolute value of vector A minus vector B. So it doesn't matter if I'm subtracting the biggest, the smaller from the bigger or the bigger from the smaller, because I'm going to take its absolute value anyway. So 5 minus 7 or 7 minus 5, the absolute value of both of those will be 2. In fact, I'm going to write that down. The absolute value of 7 minus 5 and the absolute value of 5 minus 7 is the absolute value of 2, which is 2. or the absolute value of -2, which is +2. So you can see that in both cases, it doesn't matter which direction I subtract because I'm taking its absolute value anyway. Okay, if I was to do this with vector diagrams, so I'm going to start here and go that far. So this is vector A. And then in the opposite direction, will be vector B. So the resultant of A plus B will be that. It looks like I subtracted, in a sense I kind of did, but like B is in the opposite direction. So adding it means I'm subtracting. It's like adding a negative. It's the same idea as subtracting. Okay. So I certainly do go this way and then go back the other way until I get to this position. That is what happens. These are very often not useful situations because often we're dealing with vectors that are not parallel to each other. So they're not either in the same direction or opposite direction. Sure, they are sometimes, but often they're not. So this is a special case of adding and subtracting vectors that's not going to be overly useful. And as I've already kind of said a few times, generally speaking, we're not drawing vectors as arrows like this and doing math with them as drawings on a page. We will develop a system by which we can do numerical calculations the way we like to do to get things exact and not be just measuring stuff. But today is a good day to just come to terms with what vectors are and try to think about them, because some of the questions that we're going to do will require a basic understanding and just an intuitive understanding of what a vector is, and that will help you solve problems moving forward. So it's still an important day, even if the kind of math we're doing today isn't going to be all that similar to stuff we're going to do moving forward. Some of the stuff we do might be a sort of applicable, but for the most part today is about understanding. So that was all parallel vectors. What about non-parallel vectors? Well, when I do non-parallel vectors, how do we add them? We call it placing them tip to tail. So I am going to attempt to get my ruler. Let's see, that's 19 degrees. If I make it 18 degrees, is that any better? Oh, it's a bit better. And about how long is that? Looks like it is 1, 2, and maybe 0.2, something like that. So if vector A, I'm thinking it's about 2.2. I'm going to come over here and draw it 2.2. 1, 2, whoops. 1, 2.2. So there's vector A. So they're in different directions. I can't just add their magnitudes. So now let's take a look at vector B. Hey, not bad. That looks like about 1.3, let's say. So what I'm going to do is I'm going to line up the tail of vector B with the tip of vector A as best as I can on this computer. And there you go. Okay, so what is my resultant vector? Well, it's from the very beginning of the path to the very end of the path. And so my resultant vector R is vector A plus vector B. And very simply, you can think of this: if you're walking to your friend's house and you go 4 blocks this way, 4 blocks that way, you walk on a diagonal through a park, and then you walk 3 more blocks some other direction. But what was the overall accumulation of your trip? The shortest path, the line, the arrow that goes from the door of your house to the door of their house, right? So ignoring the actual path that you took, just where you started and where you ended up, a straight line, a straight path to that. That's what the resultant vector is when you add vectors. And we call that placing them tip to tail. So then what about subtracting vectors? All right, let's line up A again. What was it, 18 degrees? So here's A. And again, it was about 2.2. Do it over here. I got a bit of space. 1, whoops. 1, 2.2. So there's vector A. So if I want to subtract vector B, what I'm actually going to do is add negative B. So B was about 1.3. So instead, I'm going to subtract B by going that way. And in this case, my resultant vector if I can get this lined up, that looks all right, is very different. So A minus B or A plus negative B. I used B with the same magnitude but the opposite direction. And you can clearly see that that A plus B is not equal to the negative of A minus B or anything strange like that. Like there's no there's no connection between adding A and B and subtracting A and B, right? They have totally different directions. There certainly are cases where there might be relationships, but generally speaking, they're very, very different vectors. Okay. Okay, and another thing that we talk about vectors, this is a really useful exercise for thinking about vectors, what they are, what their nature is, and coming and starting to just think in terms of vectors is with these kinds of vector diagrams. Something I haven't talked about yet is that vectors don't exist in a particular position. So before I get into any of these questions, I want to talk about this. Something that is true given this diagram is vector PQ is exactly equal to vector SR. So this is counterintuitive often because they're in different places. They're in different positions. One's up at the top, one's up at the bottom, so they're obviously different. But vectors don't exist in a particular position in space. Vectors exist as a magnitude and a direction. And as long as their magnitude or their length, if their drawings are the same, and as long as their directions are the same, they are equal or equivalent vectors. So those two vectors are equal even though they exist in different positions in this diagram. Just like if I start at 7 and run 5 kilometers to 12, or I start at 8 and run 5 kilometers to 13, in both cases, I've run 5 kilometers in the same direction. So my resultant vector in both those cases is exactly the same, right? As long as I'm running in the same direction, obviously. So that's how you can think of it. But this is a tricky thing for a lot of people, and it takes some time to really come to terms with and remember that this is the case, and that vectors don't exist in a position in space. You can move them around. You can take their tail and start it wherever you want. And if you end up in the same position, then the vectors are the same. So let's take a look at some of these. Find a single vector that is equivalent to each of the following. So from S to T, now I can do this easily. From S to T, and then from is that vector, and then from T to R is that vector. So the resultant vector is just where I started to where I ended up, which is S to R. But you can see that when I'm adding in this situation, which we often won't be, but if I am, because I ended the first one at T, and then I started the next one at T, the resultant vector will just be from S to R, right? But here's the thing that's counterintuitive. S to R, this is one of the possible answers. Another possible answer would be PQ. And a lot of people would say, that doesn't make any sense. You started at S and you ended at R. So the correct answer is SR, but no, PQ is the same vector because it has the same magnitude and same direction. Or I could say equal to negative QP. So something you might be doing as you're doing the practice for over the next few days, but in particular today, is not just getting a single answer that's the most obvious, but thinking about what other vectors are also equal to the answer that I came up with. And that will hopefully help you break that intuition that ST plus TR just matter of fact equals SR. That's only one of the answers. There are other answers. Okay. So SQ plus SR, in this case, I'm going from S to Q and then Q to R. So again, this would be equal to SR, and equal to the other ones, PQ or negative QP or negative RS or any of those other ones. And then ST to TS. So I go ST and then I go TS and I ended up going nowhere. So that is equal to the zero vector, not equal to S or something like that. That is equal to the zero vector. Okay, what if I'm doing a whole bunch? I think it's useful to think of these in two different ways. So from S to R, then from R to T, I'm actually following the path here. Then from S to T, but people would say, but hold on, I'm not at S. How do I add ST? But ST is this vector. So if I take this vector and I put its tail here and I move it like that, then that's the same as going from S to T is the same as going from T to Q. And then plus QP, well, I am actually at Q now if I think of it that way. So if I go to P, I go there. So I started at S and I ended at P. So my resultant vector here is going to be SP. So following the path like that is a good starting place for thinking about vectors, but it's not always going to work. And in fact, in some cases, it's going to sort of make us make mistakes. Okay. So the other way we can think of it, SR plus RT, because I ended at R and started at, and then started at R, this is going to be equal to ST. And instead of ST, I'm going to come up with an equivalent vector. So this vector and this vector are the same. So this is like plus TQ. Instead of adding ST, I'm going to add TQ because those vectors are equal. So this ends up being SQ because now I've ended at T and started at T. And SQ plus QP is SP. So I took a roundabout path, but the resultant vector of the addition of all those vectors is SP. Okay, now I'm subtracting a vector, PT minus ST. Now, instead of subtracting a vector like this, the easiest way to think about it is always going to be adding the opposite. So this is a really useful way of thinking about it. Something actually we're going to use for some really important ideas later on. Subtracting vectors can be a bit of a strange thing. So adding the opposite often is a much more intuitive or much easier way of thinking about things. So I am going from PT. So P to T. And then I am adding negative TS. So what does that mean? Sorry, I want to add negative ST, which means I turn this into adding TS. So if I'm adding a negative, or I change it to adding the negative ST, which is TS. So I'm not subtracting TS, I'm adding TS. ST goes this way. So if I subtract it, I'm going the same magnitude, but I'm going this way, which is adding TS. So PT adding TS, that makes more sense. And now the resultant vector in this case is PS. So I'm adding the negative of it, but then I can actually change the negative of ST to TS, and that's how I can make more sense of subtracting vectors. Okay. So how would I apply it in this case? I'm going to get PS. Instead of subtracting RS, I'm going to add SR. So that's what we mean by add the opposite. And then add, instead of subtracting PT, I'm going to add TP. So PS to SR is PR. What's another way I could write TP? Let's take a look here. So I've gone from P to R, and then I'm adding TP, but TP looks like the same as RT. Those are equal. So I could also write this as equal PR plus RT. Now you don't have to show this, that TP is equal to RT, to get those R's lined up the way I'm doing. You don't have to show that, but you probably do have to think that. And so my resultant vector in this case is going to be vector PT. You probably do have to think that way in order to answer questions like these. You've got to figure out an equivalent vector to RT, because what you're going to think of is, wait a minute, I went from P to R, and now it wants me to add T. But I'm not at T, I'm at R. So I can't add T. This is what people think, but vectors don't exist in a particular position in space. So even though TP is this vector, I can actually take that vector and move it, and it becomes RT. And they are equal vectors, so I can replace one with the other. That's what vectors are all about. Okay, so these vector diagrams are a really useful way of starting to think about vectors and coming to terms with, what their true nature is. Okay, a couple more things. Multiplying a vector by a scalar. This is intuitive. It's not too bad. When vector A is multiplied by scalar k, the resultant vector is k times vector A, so just Ka. It has a magnitude of the magnitude of k times the magnitude of A, so k might just be the number 2, and A is a vector, so it's not just a number. It has magnitude and direction, but it might have a magnitude of 3, and so 2 times 3 is 6. So A would have so the result would have a magnitude of 6, and it would be in the same direction as A, as long as k is positive. Okay. Again, I think this is fairly intuitive. So A is multiplied by scalar k. The resultant vector would be Ka. It has a magnitude of k times magnitude of A, as I just said. It has the same direction as A if k is positive, or opposite direction of A if K is negative. So if you multiply by a negative, you're changing the direction of the vector. And the resultant vector Ka is going to always be parallel to A, either in the same direction or opposite directions. Okay. I guess we are going to talk about this definition here, collinear. This is what I was referring to before as one of the other words we use for parallel. And people are going to ask, well, why do we sometimes call them parallel and why do we sometimes call them collinear? There maybe are subtle differences, but really for us, they're not relevant. So we tend to use these interchangeably. So the definition of collinear is vectors are collinear if they lie on a straight line when they are arranged tip to tail, which would be an appropriate definition for parallel as well. One of the differences maybe two lines are parallel that go on forever. They don't have a tip and a tail, whereas vectors have a start and an end. Lines that we talk about in grade 9 and grade 10 don't have a start and a finish. But again, we talk about vectors as parallel. We talk about lines as parallel. We talk about vectors as collinear. We sometimes talk about lines as collinear, lines that go on forever. So these do tend to be interchangeable definitions or terms. Okay, so you can think of collinear as another way of saying parallel. If vector A and vector B are non-zero vectors and they are parallel, then they are also collinear and they are scalar multiples of each other. Okay, so if I have two vectors, I'm going to draw a couple of vectors here. Okay, and I'm going to draw this. The first one I'm going to draw to be that far, and the next one to be that far. So I drew that about 3/4 the length of the first one. Okay, so that means B would be equal to 3/4 of A. That's just how I drew it. Again, it's not going to be perfectly accurate, but we can talk about it like this. So this is a scalar multiple. I multiplied the scalar, which is 3/4 or 0.75. I multiplied that times a vector. They're in the same direction, so they're equal to each other. Or I could say A is equal to 4/3 B. And I can rearrange that formula just fine, just like that. Okay, so that's some quick examples of scalar multiplication. We're going to do a lot more work with that. It's going to come up a lot, but again, I think it's fairly intuitive. Let's see, properties of scalar multiplication. This is one thing that until we get more operations and we dig deeper into this, it may not make a whole lot of sense. But when you perform an operation on a vector, the result will sometimes be a vector and sometimes be a scalar. And which one of those things it is really important to understand it and to have a good, strong sense of, strong understanding of. Okay, so in this case, when we did some operations before, and we didn't talk about it. So let's talk about that before we get here. If I add two vectors together, the result is a vector, whether they're collinear or not, whether they're parallel or not, whether they're in the same direction or not. If I add vector A and vector B, the result is a vector, the resultant vector. Okay. If I subtract two vectors, the result is a vector. So scalar multiplication, the result of scalar multiplication is a vector. It has a direction. It doesn't lose its direction. As we said, it's either in the same direction as the original vector or the opposite if the scalar that you're multiplying by is negative. Okay. So this is an important thing to know, because some of the other operations that we're going to talk about, that's not always true. And then this is something we're going to talk a lot about, different properties, mathematical properties of operations, whether or not they hold. And in this case, distributive property does hold. So if I have a scalar K times vector A plus vector B, that is equal to K times vector A plus K times vector B. And you're probably thinking, well, yeah, of course it does. That's what the distributive property means. But here's the thing, and this is a strange thing. And if you were actually studying math and you were taking what we call pure math courses, you would explore more and more about different number systems and different areas of mathematics have different rules. And sometimes distributive property holds and sometimes it doesn't. And we'll see that a little bit as well. Distributive property doesn't always hold true for all operations. In fact, we've seen that even in exponents, where a plus b squared, whoops, like that, does not equal a squared plus b squared. So exponents are not distributive. But you would say to yourself, yeah, but this is the same addition distributive that we've been doing since grade 9. So of course it's true, but it's not so easy to say of course it's true, because vectors don't always behave the way our numbers that we're used to do. So that's something that you really have to get used to. Associative property also holds. So if I have a, this is a scalar k, and then another scalar n times a is equal to k times n times vector a. Okay, and that's the associative property, and it does hold for scalar multiplication. Okay. I'm not sure you're necessarily going to memorize all of these properties, but some of them are going to be important, and there are some that when we learn they're not true, those ones are important to remember and not try to use them, because that does happen once in a while. And we'll see that a little bit moving forward in the next few days. Okay, so here's a quick example of how we could just simplify this. This is just using those properties. Okay, so 2 times vector A plus vector B would be 2 vector A plus 2 vector B, minus 3 times vector A minus 2 times vector B will be minus 3 vector A plus 6 vector B. And I can collect like terms. That all of this, they look like they're just variables. They're not quite the same as just variables because they're vectors, but they are variables that are representing vectors. So this looks like negative A plus 8, negative vector A plus 8 vector B. Okay, all right. Example 4, given the diagram, state 3 equivalent vectors. This is probably pretty straightforward, but again, there's maybe a little bit of a deeper understanding that's going on here if you really push yourself and start to think about it. We're not just saying that they look like each other. We are saying they are equal. They are exactly the same vector. When I use the equal sign in mathematics, it means they are the same. I can replace one with the other. So if I start with vector FA, it's equal to EB. I don't just mean they're in the same direction. I mean they are the same. One of them's over here, the other one's over here. So you're saying, no, they're not the same, they're different. That's that one and that's that one. And I'm saying, no, that's wrong. When you talk about them as a vector, which is what I'm doing when I'm using this notation, I am saying they are the same, and this is equal to vector DC. Also, it only said to find 3, but I'm going to do more. Equal to vector negative CD, because I went the opposite direction, but I put a negative in front of it, right? So I could come up with other vectors as well that are equivalent to vector FA. How about 6 parallel vectors? Okay, so vector AB is parallel to vector AC, which is parallel to vector BC, which is parallel to vector CB, because they're not in the same direction, but they're parallel, which is parallel to vector FE or EF or DF. And I don't know, is that 6 yet? I don't know how many we're supposed to do, but that's a list of a bunch of parallel vectors. Now, if you were stating that 2 vectors were parallel, you would state it like this: AB parallel to vector BA, or whatever other vector. You would use that symbol as the parallel symbol. I just wrote them out as a list because when I'm writing 6 in a row, it gets to be a jumbled mess if I use the parallel symbol every single time. But generally, if you're stating 2 vectors are parallel to each other, we would show it like that. Okay, but what's important is direction doesn't matter, size doesn't matter, just any vector that's parallel is what we're looking for there. Okay, and then 2 opposite vectors. So we're not just saying two vectors in opposite directions. That's another question that you could ask. Two vectors that are in opposite directions, but this means two opposite vectors. So AB is and AB went this way is opposite of EF because they're the same length but opposite directions. Or CA is opposite FD. So CA goes this way and FD goes that way. They're parallel, so they are in opposite directions, and they're the same magnitude, so they are opposite vectors. Okay, finally, last thing that we're going to talk about for the question below, and we're using the same diagram above. Okay, so it's this diagram again, but we're saying vector M is AB, vector N is CD, and it's also telling us that BC is twice AB, so double the magnitude, same direction. Okay, and then this is just a question that makes us think about vectors. It says determine each of the following in terms of M and N, right? So I'm going to look at FE, and I'm going to come up here and I'm going to say, well, FE is equivalent to AB. So I'm going to start with that. So FE is equal to AB. Well, and AB is vector M. This one, these questions are tricky for a couple of reasons. One is just the style of thinking, and you have to be a bit creative sometimes. You have to get used to vectors. That's one of the reasons. But the other reason is just generally like writing it in terms of N. Finding an equivalent vector AB would probably be easy, but always turning it into something in terms of M and N, that is something that is new and quite different, right? So practice, practice, practice. Okay, BA is equivalent to negative AB, and AB is vector N, or M, so this is equivalent to negative vector M. AC, this is a good one, is equal to, so I've got is equal to vector AB plus vector BC. Why did I choose those two vectors? Because I've got AB and I've got BC here. And so BC is 2AB. You wouldn't have to show all these steps. Whoops, 2AB. And AB is vector M. So this is M plus 2M, which is 3M. So that's how I've written it in terms of vector M. In this case, I didn't need N, but I've written it in terms of vector M, right? Okay. AD. So let's see. I can turn, let's look at the diagram. I've got A, and there's different ways you can do this. But I'm going to go A to C, and then I'm going to go C to D, and that is AD. Even though that's not a line on here, I'm writing it out in terms of the lines that I have. So I have to figure out a path that is actually in the diagram, and then I'm going to come up with what those vectors are in terms of M and N. So I'm going to write this out as AC plus CD. Well, AC I've already figured out is 3M. And CD is N. That was given by definition. So because I've already calculated AC these are misnumbered. So that should be ABC. But because I already calculated AC there, I can use that answer. I don't have to redo all of that, okay? So plus CD, which is N, and I'm done. I can't simplify that any further. M and N are obviously different vectors, so I can't add them together just like terms, just like we did in grade 9, so I'm done. Okay, and DB. So DB is this, but I need to do it in terms of vectors that I have in terms of M and N. So I'm going to turn that into DC. I know CD, but I can write that as DC, and then CB, right? So to go from D to B, I can change this to DC plus CB. And DC, so N is CD, so DC is negative N. And CB is negative BC. M is AB. So this is 2M. So BC is 2M, but I'm going CB. If you wanted, you could add extra steps in here. But this is plus negative 2M. So negative 2M minus N. And there's no real reason to do this, but I could factor it because we talked about distributive property. This is a scalar of negative 1 that's in front now. So I can multiply it in to get negative 2M times negative N. So factoring it out works the same way as factoring as we've done in algebra since grade 9. That would hold true as well because the distributive property holds true. So that's an introduction to vectors. I can't express how important it is that you get used to thinking about vectors the way they are, that they don't exist in a particular position in space, that their tail, where they start, can be moved around, and how they're made up of these two parts, direction as well as magnitude. And we're going to start doing some other operations. Most of what we've done today, I think, is intuitive. I think that these vector diagram questions are harder than they look and do require some real practice and thinking through, and they require creativity. There are other diagrams that are very different from this parallelogram. And so just practicing with different diagrams and different types of questions is how you're going to start to think about those things. But this is, it may seem simple, but it's actually a lot more different from the kind of math we've done in the past than it looks like. We just finished calculus, and this is a whole different world from that. So it's a very just turn on a dime way of thinking about mathematics. And you're going to see over the next few days, as we look at other operations and other properties of vectors, how different it is, and how many simple things that we take for granted so far in mathematics, how different they actually are when we all of a sudden introduce vectors that have direction. So it's important to work through this practice and not take for granted that this is not as simple as it seems. All of these seem like intuitive ideas of tip to tail addition, and subtracting is adding the opposite. Those all seem intuitive, but we've seen this before. We start to add more levels of complexity and it starts to muddle things up. Okay, but that is our introduction to vectors and some simple vector addition and scalar multiplication.